so this video is going to be about concave spherical mirrors. It's section 24.2 in your book. A concave spherical mirror is exactly what it sounds like. It is a mirror that is essentially curved like a sphere. An imaginary line that goes right through the center is called the optic axis. It's also called the principal axis, and that is the correct spelling. It's P-A-L as in the primary one. P-L-E is like a principle, like a rule or an idea. P-A-L is, of course, primary, like the head of a school is the primary person. There are several important points we want to talk about. First is a point I'm going to call C. C is the center of curvature. If this was just flat like a circle, instead of being three-dimensional, it would, of course, be the center of that circle. And halfway, oh, not halfway, let's go to this distance from here to here. And I'm going to draw kind of an imaginary line straight right here. Is called the radius of curvature, and that is exactly what it sounds like. There is a point halfway between the center of curvature and the mirror itself. That is the focal point, capital F. That is the focal point. And finally, this distance from the mirror to the focal point, lowercase f, is the focal length. Okay. A very important idea for a concave spherical mirror or for convex spherical mirror is the fact that the focal length f is equal to 1/2 r. The focal length is exactly half the radius of curvature. Okay. So we've got some really important things we need to know. Center of curvature, radius of curvature, the focal point, which is exactly halfway between the center of curvature and the mirror, and of course the focal length, which is exactly half the radius. Okay. Let's look at how the rays behave. We actually usually treat this as if it's flat instead of curved. And that may seem really strange because I just said that it was a curved spherical mirror. But the rules that we're going to write down are rules that only hold true for small angles or for relatively small part of the curvature. If you have a very curved mirror, you get something called spherical aberration. I'll talk about that a little bit more. So our mirror, it is curved, just like that. And of course, we're going to have our optical axis right through the middle. Okay. So how do they work? Well, let's just make up some points here. Let me label something. Let's let, and we might as well draw this true to size, even though I don't know. So there's that. And there's that. So here's my center of curvature. There's halfway between. That would be my focal point. Okay. We want to just look at what we call I'm not sure, sort of the primary rays or principal rays. How does this type of mirror work? Well, any ray parallel to the optic axis is reflected through F. That's our first rule. Rule number 1. Any ray parallel to the axis is reflected through F. So, if I draw a ray coming in, and when I do this, I want to draw it all the way to that dotted line. I know that seems weird. And it will reflect through F. Okay. If I have another parallel ray, let's draw one down here someplace. I think you can see why we call that point the focal point. If we have a spherical mirror and we took it outside, the rays from the sun are all virtually parallel. So if we held it up, it would form an image of the sun at the focal point. You get a really, really hot spot right there. In fact, lenses like this can actually start fires and things by concentrating the rays of the sun. I've seen that done for lab demonstrations. Okay. So any ray that is initially parallel to the axis is reflected through F. Okay? Now, light rays are completely reversible. So there is a corollary to that, which basically says any ray through F is reflected parallel. Okay, I could turn these arrows and say this was incoming through F, it would reflect parallel. Or if this ray was going this way through F, it would reflect parallel because the path of a ray of light is completely reversible. Okay. One interesting result of that is if I were to take something like a light bulb and I put the light bulb right here, of course it would send light out in all directions, but a large percentage, all of those that hit this mirror, would reflect back in a beam. And that's why we put those curved mirrors behind your headlights in your car, is rather than make light that just goes out in all directions, they help focus a lot, not all of the light, but a lot of that light into a nice parallel beam. For spherical mirrors, this is in your notes if you print off the notes, those statements right there are true for what we call paraxial rays, or rays that are almost, that make small angles with this axis, as long as we don't get real crazy large angles, okay? If you get larger angles, we'll get that spherical aberration. However, if instead of a spherical mirror, we were to use a parabolic mirror, those statements would be 100% true. Mirrors used in things like telescopes, like the Hubble telescope and things, those are not spherical mirrors. Those are parabolic mirrors, which have, in fact, a very precise focal point. Okay. There are lots of ways to do ray tracing, and you'll do a little bit of that on your homework. But most of the time, it's easier to solve these types of problems to locate the image. I can draw you how I might locate an image with ray diagrams, but it's easier to do the lens mirror equations. You're going to find those really pretty easy. So let's look at the lens mirror equations. One really nice thing is these equations work for a lens or for a mirror. It's nice we have two different types of optical instruments, lenses and mirrors, but they have the same equations. One is 1 over s plus 1 over s prime equals 1 over f. S is the object distance. I want to say on the geometric optics lab, they use DO for the object distance, and that's okay. Different text, different labeling. S prime is the image distance. And I want to say the lab uses DI. Those are definitely also used in some textbooks, especially high school textbooks will tend to use that notation. And of course, F we know is the focal length. One of the things we have not mentioned about yet is that focal lengths can be positive or negative. For a concave mirror like we just looked at, it's a positive focal length. When we talk about the convex mirrors, we'll find out that it has a negative focal length. But that's one of our equations. It's a very important equation. The other equation is for magnification. Magnification is simply the ratio of the image height to the object height, but it also happens to be equal to the negative of the image distance over the object distance. So we have multiple ways to find that. Y, of course, is the object height. In your geometric optics lab, they use HO. Y prime is the image height. And they use HI, looks like the word high, on the lab. So don't let that confuse you. It's really easy. If the magnification is positive, the object will have an upright image. So anytime we find out that the magnification is greater than 0, we know two things. We know that the object is upright. We also know that it's virtual. Anytime you have an upright image, you have a virtual image. You do not actually have light at that point. You just have light that appears to come from that point. Anytime the magnification is negative, the object is inverted. It looks upside down. When an object is upside down, that's actually a real image. A real image occurs when light is actually focused there. Your eyes form real images on your retina, and the pictures on your retina are actually upside down. We'll talk about that when we get to lenses. Okay, so all of this is really important. If you are capable of printing out my handwritten notes, you may have all of that written down for you already. I want to look at an example. We'll use these formulas, but I've got to erase them to make room. Okay, it says a lamp. By lamp, we're probably really talking about just the filament, is 10 centimeters in front of a concave mirror which forms an image 3 meters in front of the mirror. First question is, what is the radius of curvature? Okay. Before we can find the radius of curvature, we're going to have to actually find the focal length. We know the radius of curvature is twice as long as the focal length. The lamp is 10 centimeters in front of the mirror. This is going to be a positive 10 centimeters because the object distance is positive if it's on the side of incoming light. We picture our mirror. Here's our object. And of course, this is the light side, so incoming light is over here. This is the dark side. Okay. It says the image is 3 meters in front of the mirror, so the image is way out here. Let's draw this a little closer. Object's up here, image is way out here somewhere. That is also going to be a positive 3 meters. I know it's going to be positive. I also actually know it's going to be a real image upside down because I'm just more familiar. But we know this has to be positive because both incoming and outgoing light are on this side. Images are positive when they're on the side of outgoing light. So I know this is also positive 3 meters. So to find the focal length, I know 1 over f equals 1 over s plus 1 over s prime. We either need to work in centimeters or we need to work in meters. I'm going to work in centimeters. So the object is at 10 centimeters. The image is at 300 centimeters. When I do the math, I find that the focal length is about 9.7 centimeters. Okay. You can add those together, take the inverse. The focal length is about 9.7 centimeters. The radius of curvature to 2 significant digits is 19 centimeters. So we've answered the first question. It was important. 2 things were really important. We need to understand signs. Objects are at positive distances when they're on the side of incoming light, which this one clearly has to be with a mirror. And images are positive, image distances are positive when the image is on the side of outgoing light. And for mirrors, incoming and outgoing light are both over here. So since the image was in front of the mirror, it had a positive. When we did our plane mirror, the image was behind and it came out negative. Okay, so we've done part A. Let's look at part B. Part B says if the lamp filament is 5 millimeters high, how tall is the image? So B says if y is equal to 5 millimeters, can you find y prime? Well, yes, because we can use the latter part of that magnification formula that said y prime over y is equal to negative s prime over s. Now, s prime and s have to have the same units, and if we do, then y prime and y will also have the same units. If that makes you uncomfortable, you can make all four have the same units. Just think about what you need to be consistent. So I'm going to say y prime in millimeters, which I don't know what that is going to be over 5 millimeters equals negative 300 centimeters over S, which was positive 10 centimeters. Remember, S prime was positive, but there's a negative sign here, okay? When I cross multiply and I solve for that, let's see what I get. I get y prime equals a negative 150 millimeters. Now, what is the negative telling me? The negative is telling me that that image is going to be inverted. It's going to be upside down. I knew that because real images are inverted, and when a mirror forms an image out in front of it, it actually is focusing the light through. That is a real image. If we prefer, we could make that into centimeters. That's 15 centimeters. The fact that it's negative tells me that the image is real, and it tells me that it's upside down. So try to link those two things in your mind. Virtual images are like you see in the bathroom mirror, a flat mirror. In virtual images, the image is always upright. In real images, it's always inverted or upside down. Okay. Part C says, what is the magnification? Well, the magnification is the easiest thing. It is simply that ratio of image to object. So negative 100, well, we need to use the same, so negative 150 millimeters over 5 millimeters is negative 30. Now, magnification does not have units because the units have to be the same here. So those are millimeters, and they always cancel out. So it's just a pure ratio or a scale factor. Okay. In this case, the image is 30 times larger and inverted. Okay. That concludes our discussion of a concave spherical mirror. I'll make another short video over the convex spherical mirrors for you.